Welcome everybody. In this video, we're going to talk about how we can use the thermal inertia of a surface or of a material to distinguish different geologic materials from one another. So what is thermal inertia? I think of this as how quickly temperature of an object equilibrates with its surroundings. The same way it takes a freight train a long time to slow down, it takes an object with a high thermal inertia a long time to change temperature. And thermal inertia depends on the heat capacity, so how well a material can hold heat, its density, and its conductivity. And so thermal inertia P is the square root of heat capacity times density times conductivity. So I love this example, the best ever example of thermal inertia. This is a thermal image, so it's collected in an infrared band, so it's more sensitive to emitted heat energy than it is to reflected solar energy. And what do you see in this image? 1, 2, 3, 4, 5 helicopters. Wait, there's no helicopter here. The only thing remaining is the shadow of the helicopter. And so the reason we still see the shadow of the helicopter, right, is because the tarmac at the airport has thermal inertia. It didn't change temperature immediately after the helicopter took off and flew away. So the shadow is still preserved. But again, we had to collect this image in a pretty long wavelength thermal band in order to see that. But it illustrates the idea. Here's another one. This is a farm field, a picture of a farm field taken at 11:30 a.m. Okay, so these blocks are all fields full of crops. This is a road, the white road, little farmhouse with some trees over here. We have a creek running down over here. But what is this thing? What is feature B? Coming through the whole picture and almost making this like oval horseshoe shape. And it seems to cut through everything. And again, I have to say, this is another thermal image. So this is taken in long wavelength, not in reflected visible. So what do we infer from this? Well, we infer that whatever this material is, it must be a bit hotter than the surrounding material, right? It's emitting more radiation in a thermal wavelength. So from the previous videos, we know it must be hotter. And sure enough, what it is, it's a sandy beach ridge, which is contrasting with more clay-rich lake bottom sediments in the center of the field. So essentially, there was a small lake here, and this was the shoreline of it, where we had a sandy beach deposited. Those beach sands are still part of the soil. Okay, of course, they're being farmed now, so we see the farmers' rows going right over them. But there's basically a lot of sand in the near surface right through here. Sand has a lower thermal inertia than clay. So the sandy shoreline is showing up as bright because it has warmed up in the middle of the day. By 11:30 a.m., the sun is up, and that sand followed the sun and warmed up very readily. In contrast, the clay-rich lake bed soil here has been slower to warm up. It's still cold from the night before, so it's showing up as dark because it's not emitting much thermal radiation. So if you think about how these changes in temperature play out over the course of a full day, we can think about how the object of a temperature might respond to solar forcing. Okay, and so if you look at this, this is a simplified plot of just radiation, no units, so very generalized. The sun does this. Sun rises at 6 a.m. It gets more and more intense until we get a peak solar radiation around noon or 1 o'clock, and then it declines by 6. In contrast, outgoing terrestrial radiation, so the amount of essentially thermal radiation put off by the Earth's surface, does this. It hits a peak, it hits a minimum right before the sun rises. That's essentially its coldest point, right? As the sun rises, it warms up, and it's emitting more and more radiation. But notice, its peak it doesn't peak at the same time as solar radiation does. Even though this is the hottest time of the day, because the surface has thermal inertia, it doesn't turn and start to cool again at the same moment the sun starts to fade. It continues to warm up a bit with those afternoon rays, and then eventually rolls over and starts to cool and emit less radiation as a result. So that's a really good example of thermal inertia. It's also a good example of how we think of surface temperature almost always in terms of how it relates to solar forcing, right? Because it's the sun that is really warming and then allowing surfaces to cool over time. So now let's think of that same idea. So here's a full 12-hour day. And we're going to start here actually at noon this time, go to 6 o'clock, midnight, 6 a.m., and then noon again. And here are 5 different materials with different thermal inertias. So here's a low thermal inertia. This one changes temperature easily. And here's a high thermal inertia. It doesn't change temperature as readily. All right, so let's look what happens. So the one with the low thermal inertia, it has a huge peak. It warms way up during the day, and then it cools very, very quickly, and it also achieves a minimum temperature that's lower than the others overnight. Then the sun rises at 6 a.m., and it warms up very quickly and gets hotter than the others. All right, so that's a low thermal inertia. It means that we get bigger temperature peaks, and they happen sooner relative to the solar forcing. So now let's look at this one, the 500. So this is a high thermal inertia. So again, coming in the afternoon, it has not heated up as much, okay, because it has a high thermal inertia, so it's tracking always closer to the mean temperature. Whoops. So it has a low, it doesn't get very hot, and then as the sun sets, it actually doesn't get that cold. It stays warmer overnight because it doesn't cool as readily. Okay, sun rises, it starts to warm again and doesn't get as hot as the others. So again, for a high thermal inertia, we see smaller temperature oscillations. We see that the peaks actually happen a little bit later than the low thermal inertia. Okay, and one more example. I think you're getting the hang of this, but here we've got midnight through to noon through to midnight. And now let's look at 2 different materials. So, and this is radiant temperature, so essentially the kind of amount of radiation that they are, or it's their temperature, basically. So here is dry soils and rocks. Sun rises at dawn. Boom, low thermal inertia, dry soil and rocks. Gets really hot and then comes back down. Water does something different. Sun rises at dawn, starts to warm slowly, doesn't get nearly as hot. It peaks later, okay, because it has a higher thermal inertia, so it peaks later, lags the sun by a while, and then starts to cool. Great, so in terms of discriminating materials, all types of materials have different thermal inertias. And as I've said in previous videos, what makes this incredibly powerful is that these are body properties of the material. So whereas materials might have different reflectance characteristics from one another, that doesn't matter if they are covered in dirt, or if they're buried a little bit below the surface, or if they're covered in moss or vegetation, right? So the thermal properties is another piece of information that you can use to diagnose and differentiate material if they are spectrally similar or if they're covered and shielded. So I want to show one final example where we're going to look at the difference between basalt and dacite. So basalt is a mafic igneous rock that's erupted from a volcano. Okay, so mafic means it's high in iron, magnesium, and calcium. Dacite is something closer to a granite or a rhyolite composition. So it has more silica, more sodium and potassium. But it's also a erupted from a volcano. And so let's look at the difference here. Thermal inertia of 530 for basalt, so it's very high. 320 for dacite, so it's very low. And so what I'm going to do now is take you to this place on Mars called Nili Patera. And at Nili Patera, what you can see is this is what we call a caldera. Notice these circular or kind of radial fractures, which really give the impression that something imploded, something kind of collapsed within and the Earth sank down. Almost like a balloon looks like when you start to deflate a balloon and it gets wrinkles in it. So on closer, and so that's typical of a large volcanic system that once it erupts, all of that magma has left the plumbing of the system, and so the surface collapses kind of into that newly open space beneath the volcano. So it looks like a collapsed caldera. Closer inspection, in fact, this is a volcano here. Find you the best imagery. So what we see here is actually a kind of eroded cinder cone. So you see this kind of roughly conical shape. Maybe there's a couple cinder cones grown together. And then you've got the kind of hollow crater in the middle. So this is the epicenter of the eruption. And from this volcano, this caldera, a lava flow has been erupted. And we can see the edge of the lava flow in this black and white image going all the way around here. Over here it's covered with dunes, and you can kind of see it extending down to here. And so one of the things planetary geologists did at Nili Patera is they wanted to map the edges of the lava flow. How far do they go? And also, how many different lava flows are there? So what they did is actually relied on different types of imagery. In particular, they had a daytime infrared image. Okay, so this is collected in thermal wavelengths. It's not reflected light from the sun, right? This is emitted light from the rock based on its temperature. So during the daytime, what they see is, if you look closely at the lava flows, one part of the flow is dark during the day, suggesting it's cold, but another part of the flow over here stays light during the day, suggesting that it has warmed up in the sunshine. Now if we switch to the nighttime infrared, whoa, they're totally switched. Daytime infrared, nighttime infrared. Daytime infrared, nighttime infrared. Okay, let's dwell on nighttime for a second. It's dark. It's freezing cold on Mars. But yet this lava flow is still pretty warm. It's still bright in a thermal image. The inference from that is that this is a basalt lava flow that has the higher thermal inertia, whereas this one that has gone ahead and cooled down quite readily overnight is probably a dacite lava flow that has a much lower thermal inertia. And that has been to some extent verified by spectral reflectance data as well. But I believe it was first noticed using this thermal infrared material. And it's a great example of how the body properties of something, its change in temperature over time relative to the sun, can be incredibly diagnostic. Great. So in summary, surfaces experience diurnal heating, right? They get cold and hot throughout the course of the day as the sun rises and falls. Thermal inertia causes a lag between that peak insolation of the sun and the peak temperature. So things with higher thermal inertia are slower to change, so they tend to lag behind the sun, and they don't get as hot. The timing and temperature change of the surfaces can reveal their thermal inertia and thus their composition. I just said that. And this can be a powerful tool when spectral signatures are not available or the object is covered. Thanks for listening, guys. Sorry this one went on and on.